This is truly a historic evening. I'm John Toole, the Executive Director and CEO of the Computer History Museum, and I want to welcome each and every one of you. And I think it's a rare occasion that we can herald Mountain View, Shockley Labs for the wonderful things they have done and celebrate the 50th anniversary with them. First thing, I want you to imagine brilliant people coming to Mountain View in a laboratory to work on something that they sort of knew a little bit about. Great physicists, great chemists, great people that really changed the life and direction of the whole industry. And we're very happy that you did that, and we're very happy that it continues to go forward. We're also very fortunate this evening, in a very special occasion, that we have so many of the original employees here tonight. And I'd ask that the original employees and their families please stand. And we'd like to give them a round of applause for their work and welcome. Thank you very much. And I loved the direction, the mission, if you will, of Shockley Labs was to engage promptly and vigorously in activities related to semiconductors. Just phenomenal. We salute you and really thank you for the major contributions you really have made for all the world. There's many people really this evening that I do want to, okay, well, we're not quite in order yet, that I wanted to thank this evening. Not on that slide are really some of the organizers, Andy and Jacques, and the team of people that have helped organize this thing. They did a terrific job, and believe me, working with people like that, I recognize what kind of a creative talent that they were, because it was a pleasure working with them, and my staff really said the same thing. SEMI played a special role with us and is really the co-host this evening, as well as sponsoring the commemorative display now hanging in the original laboratory. And the original employees have signed that, and I hope you had a chance to look at that downstairs, because it's quite a wonderful commemorative display. Sponsors for tonight's event, and I want to thank them, the Gordon and Betty Moore Foundation. Gordon and Betty were not able to make it this evening. They're in Hawaii, but they send their regards to all of us. Yeah, right, as it rains and rains. The Semiconductor Industry Association and George Scalise was also wonderful, and TJ Rogers and Cypress Semiconductor. We thank them all for sponsoring tonight's event. A special thanks to Stanford University as well, who really have helped promote this event and have been very much of a collaborator with us in many of our activities in preserving computing history. I'd like to say thank you to them. And a special thanks to the Mountain View Historical Society and the City of Mountain View for their encouragement and participation. And with that, I wanted to bring up the mayor of Mountain View, Nick Galeotto, who is also the president of the Mountain View Historical Society, who has a presentation to make.
It's interesting. Yesterday I had the extreme pleasure of being over at the original site of the Shockley Lab at 391 San Antonio Road. And there, amidst the produce of the present occupant of the premises, we had the unveiling of the display, that part of which you see downstairs. And what's really interesting is I note that the original Shockley Lab was started in the modest former fruit packing shed owned by Shockley. So it's kind of come full circle in the sense of the original fruit packing and today's fruit at the produce place. The pleasure that I really had was being there with many of the original employees, the scientists and engineers that were the original movers and shakers of what has now become the Silicon Valley. And I want to boast on the placard downstairs, I want to boast that the statement of the birthplace of Silicon Valley is disputed between us and the city of Palo Alto. But since it's in writing downstairs, it must be true. It is Mountain View. I have a proclamation to present on this occasion, and one of the hardest things for a politician is not to talk. So I could read through this whole thing, which certainly is deserving, but I will leave this up here for people to read afterwards. And in the meantime, I would like to do a little condensing, if you will, of the content. Whereas the Shockley Laboratory, located at 391 San Antonio Road in Mountain View, begot the Fairchild era, and whereas Fairchild begot the semiconductor and high-tech industry of Silicon Valley, now therefore I, as mayor of the city of Mountain View, along with my colleagues on the city council, do hereby join with the Computer History Museum, SIMI, and the Chamber and the Mountain View Historical Association in recognizing the 50th anniversary of the founding of Shockley Semiconductor Laboratory in the city of Mountain View, acknowledging the pioneering contributions of the scientists and engineers who worked there, and marking this pivotal event in the history of our region. So with that, I'm very, very proud, as I was yesterday, to be amongst some of the original members of that organization, and tonight to be amongst how far out that has spread, the people that now represent. When you look at the chart downstairs and you see the organizations that have sprung out, if you will, from the Shockley Lab, the different names that are out there, many of them, of course, are not with us any longer. These names are like Ream and so forth, but they were a presence. They were an important presence, and they, of course, tie back to the Shockley Lab, which takes us into the future as well as the present. So I think there can be nothing more positive for the city of Mountain View than to be part of what started in the Shockley Lab and has spread to what exists today in the true Silicon Valley. So with that, John, I'd like to give you...
Thank you. We'll spread that around. Thank you, Nick. Thank you very much. We're very proud to be in Mountain View, and so is the Computer History Museum, for what we represent and working together with the industry and all the other people around. Before I really go into introducing our moderator, I wanted to say a couple of things about the Computer History Museum, some things perhaps you haven't heard. Because it's really a special way, a community, of building a community to share the talents, stories, and histories. Our collection is phenomenal. I hope most of you saw our visible storage downstairs. That's probably less than 10% of what we have in our collection. The other half of the building right now is being used for storage, and our plan is to build that out into a timeline of computing history, which takes time, talent, and money, of course. Our museum is only in our first phase, and there's a lot more to come in a lot of different ways. Our exhibits, both physical and on the web. Please take a look at our website, and over the next couple of years, you're going to see an increasingly new kinds of concepts of what's going to be available. In fact, if you look at our History of Computer Chess exhibit downstairs, on the website, you'll see all kinds of oral histories from all the people that we have done. And needless to say, we think oral histories are very important for our collection, as well as collaborating with many of the other stellar institutions around the country that are actually doing the same thing. We are still a collecting museum. We have the largest collection of artifacts in the world. And tonight I want to put a call out for all of you Shockley employees that we'd be very interested in talking to you. Now, don't just send a truckload of stuff at us, please. Unless it's really, really good, which we may take it. Tell us what you have. We'd be very, very interested in talking to you. The last thing I want to talk about the museum is the communities we serve, the people, the donors, the contributors, the historians, all of which is building something special here in Silicon Valley in our way of thinking. In addition, we're building other types of communities, technical communities, that are part of our organization. For example, let me highlight two things. One is the restoration projects that you may have not seen yet. We have a PDP-1 just off the lobby. We're going to make that into a complete public display here very shortly. PDP-1 was the 1960s first machine from Digital Equipment Corporation. And IBM 1401, another project that we've started back in the back rooms. one that goes clankety-clank, so to speak. It was a very popular machine also in the 60s. But it'll give people an experience of what life was like in that era, plus the lessons that you really learned over time. And I think recording those stories, recording the history, and then digging through that material to make sense out of it, and to help people that are about the present and about the future. That's kind of what we're all about. And we'll be building a formal education program beginning next year, and eventually a research program, all of which you're going to see sights and sounds and action, because that's kind of what I think's made us and brought us here today. One thing I wanted to bring to this group and sort of announce this evening to this group is the Semiconductor Special Interest Group. This has been in the mill for being formed for over 2 years in the background. It brings together academia and industry people to advise the museum on what we should collect, what we should exhibit, and to help us go do that. And we've really formed that. Dave House and I have been the pseudo-chairman of the such. People like Jeff Katz, who is here this evening, who was one of our docents as well, is on the steering committee. And we ask if anybody is really interested in helping with that, to please sign up, give us your name, because we're going to be expanding that over the next couple of years, and it's going to be substantial because down the road, we're going to be putting some theme rooms in, and those theme rooms are going to be important. And of course, you may ask, well, why semiconductors? This is the Computer History Museum. Well, this is Computing History Museum with a big C, and it involves a lot of things, both in the breadth of information technology and the depth of what really makes us important and allowed computing to be important. And semiconductors is certainly one of those fundamental things. And I'm proud to have worked myself in the semiconductor industry from the funding side at ARPA for many years, and it was really an eye-opener with the talent and the people that we saw for many of those years. So I welcome you all to the Special Interest Group, SIG, and please sign up if you're interested. And of course, my last message is, please help with artifacts. Become a core member of the museum. There's material out there because it takes support to really make that happen. And I'm proud to ask for that because that's what it takes, a grassroots effort, and I think you can really help us do that. And of course, become a volunteer because there's all kinds of interesting, exciting projects that you can help us define as we go forward. So with that little bit of background, I want to go back now to the main event of this evening with a terrific panel that is really heralding that which each and every one of you have contributed to, probably in the audience, and especially those Shockley employees. I want to introduce Michael Riordan, who himself is a physicist, another physicist that we have up here. He got his PhD in 1973 from MIT, and he also worked locally as a grad student and postdoc in the 1970s on MIT SLAC experiments that discovered quarks. And then he wrote about quarks. He decided it was important to write about, and in his book, The Hunting of the Quark, which, of course, everyone has probably read in this room. Certainly the Shockley employees, I'm sure, have, Michael. But then he turned to history of physics and technology, okay? So he has a special, unique opportunity to look at some of the technology, the implications and the social implications of that in the 1990s. And he teaches history of physics and technology at Stanford and UCSC. And of course, he's probably well known for his being co-author of Crystal Fire, which is widely viewed as the definitive history of the transistor, which was crucial to the rise of Silicon Valley. And you'll hear more about that as time goes on. And he won a number of awards, which I won't enumerate, but certainly one more than qualified to lead and moderate tonight's panel. Michael, let me turn it over to you. Welcome.
Thank you, John, for that warm introduction. And let me say that as a devotee of semiconductor history, I'm delighted to see such a room-filling audience here to look at the history of what is, from the general public standpoint, a rather obscure company. But it's a company that has had an enormous impact. I think it's safe to say that without Shockley Semiconductor Laboratories, there would not be this phenomenon we call Silicon Valley, or it wouldn't be here in the Santa Clara Valley. It was really the Shockley Semiconductor Laboratories that acted as the catalyst to bring together the technology, the silicon technology basic to the integrated circuit, and the men that would implement that technology at Fairchild Semiconductor. And I'd like to give a little run through of the history so that people understand what it is we're actually talking about here. So the history goes back to, begins with the invention of the transistor at Bell Telephone Labs in December of 1947. This slide here is the cover of Electronics magazine in September 1948, where they call it the crystal triode, the revolutionary amplifier. And at the center of that photo is William Shockley, who is the central figure of the phenomenon we'll be discussing tonight. Behind him are John Bardeen and Walter Brattain, who actually invented the transistor that Shockley is looking at through that microscope at the laboratory bench. Shockley was the leader of this group that made the invention at Bell Labs, but he did not have much of an inventive contribution to that particular device. In fact, at about 25 years later, at the silver anniversary of the invention of the transistor, he said, "My elation with the group's success was tempered by not being one of the inventors. I was frustrated that my own personal efforts had not resulted in a significant inventive contribution of my own," end of quote. Well, that led him, about a month later, to conceive what is called the junction transistor. And this is the transistor that began making its way out into industry, into commerce during the 1950s. Briefly, this is probably the most technical slide I will show. This is a 3-layer sandwich of N-type, P-type, and N-type germanium, not silicon. The initial transistors, both the point contact version of Bardeen and Brattain and this junction transistor, were made with germanium, which was simpler to work with. It melted at a lower temperature, it was less refractive, it did not interact with the walls of the crucible, and other reasons. And the three elements of this, the N-type is germanium or silicon that has a slight excess of electrons. The P-type has a slight deficit of electrons. And in this case, the P-type base acts as the kind of a grid, an analog of a grid in a cathode tube, modulating the current flowing left to right in this particular image. And you see below the first version of that realized at Bell Labs in 1951. It took 3 years to actually make a very high-quality version of this junction transistor. And Shockley didn't have to share the limelight in this. Here he is at the blackboard on July 4th, 1951, illustrating the theory behind the junction transistor. Well, I'd like to talk about another aspect of Shockley's background. This is a photo I found of him in the Stanford archives in World War II. It's taken, I think, in 1944 in Salina, Kansas, where he was advising the training program for B-29 bombing. And the World War II experience has had an enormous impact, especially during the ensuing decades. For one, people like Shockley learned how to work in multidisciplinary, mission-oriented research groups, where not only physicists, but electrical engineers, chemists, metallurgists were involved in a group effort. And in fact, when he came back to Bell Labs after World War II, he put together such a group at Bell Labs that invented the transistor and other devices, and it was phenomenally successful. The other aspect of this photo is that he was involved with what is called operations research, which put very simply is applying the scientific method to military operations, getting reliable data, analyzing it, and using it to improve military operations. Well, along with a number of other aficionados of operations research, Shockley began applying that philosophy to broader areas of life. And in fact, he gave a talk in 1954 called On the Statistics of Individual Variations of Productivity in Research Laboratories. And this was published in the Proceedings of the IRE in 1957. And it reads like a business plan for Shockley Semiconductor Laboratories. To make it very simple, the idea he had in mind was to find those few employees. You'll see this graph in the lower right corner. And at the very far right of that graph, a very few employees are responsible for a large fraction of the productivity in terms of patenting and publishing. And he determined that he would find and bring those individuals together in a company that he would act as the leader. This is really the business plan for Shockley Semiconductor Laboratories. All right. To finance that effort, he spent most of the summer of 1955 looking to people like the Rockefellers, Raytheon, and finally found Arnold Beckman, a fellow alumnus of Caltech, to finance the operation in September of 1955. They signed an agreement, and I have here a quote of what they had in plan to do. They inked a contract in early September 1955, and it says, the initial project contemplated is the production of diffused-based transistors. What are diffused-based transistors? Well, to answer that, we have to go back to Bell Labs, the fount of most of this technology that was being developed for semiconductors. And you see in this photo 3 scientists from Bell Labs. I think they're all chemists. At the left is Calvin Fuller, who pioneered the use of diffusion. The use of diffusion furnaces like that object behind him in this photo to impregnate a very narrow layers on the surface of silicon and germanium wafers, the basis of the industry to this date. And by making very narrow layers, you could get to very high frequencies. The frequency is roughly inversely proportional to the thickness of that base layer that I showed you earlier. And you could get layers like a micron or two thick in the mid-1950s using diffusion technology. The other 2 gentlemen are Carl Frosch and Link Derrick. They were the ones that discovered that you could passivate the surface of silicon using a silicon dioxide layer and use that layer to pattern the surface of the wafer. Now, there can't be anything more central than diffusion and the use of the silicon dioxide layer to the technology that would emerge from Silicon Valley. But none of the companies were using that in the mid-1950s, 1955, when Shockley came out here to start his company. Anyway, over a period of about 1 year, he gathered together not just physicists, but chemists, electrical engineers, metallurgists, and we see them here together at a shot that has been variously described as being Dinah's Shack or Ricky's Hyatt House. I think it was Ricky's Inn at the time, to celebrate the announcement of Shockley's winning the 1956 Nobel Prize. This was taken on November 1st, 1956, just after the announcement. And we see, this is an iconic photograph of the origins of Silicon Valley. We see several of the major players. At the head of the table, of course, is Shockley lifting a glass. And at the center behind is Robert Noyce. To the right is Jay Last, one of the people who's on the panel today. And at the far left, you can see in profile Gordon Moore, and next to him Sheldon Roberts. So 4 of the 8 founders of Fairchild Semiconductor can be seen in this photograph here. Well, I came out here, and none but Noyce really had any significant experience in semiconductor technology. And they began setting up shop, building diffusion furnaces, learning the technology that came out with quite a helping hand from Bell Labs. But within a year after this photo was taken, the 8 of the key founders, 8 of the key members of that technical staff for Shockley Semiconductor Labs left to found their own company, Fairchild Semiconductor, about 1.5 miles down the road at 844 East Charleston Road. It's right across from a Sun Microsystems plant today, and until recently it was the home of a repo depot. You can see Shockley kept fairly detailed diaries of his activities, and a page of this can be found again in the Stanford Archives, the Shockley collection. Wednesday on the 18th of September, group resigns. All right. The very next day, Beckman came up to try to talk them out of it, and Jay Last, I think, has notes of that actual meeting. But on the 19th of September, the 8 dissidents, as Shockley called them, signed a contract with Fairchild Camera and Instrument to start a semiconductor company focused on the practical goal of actually making transistors. And that became the first successful semiconductor company in the Valley. Shockley Semiconductor itself was the first semiconductor company in the Valley, but as far as I can tell, it never made a profit. whereas Fairchild Semiconductor had silicon transistors in production by late 1958. I think Jay just told me it was by August of 1958. And they were operating in the black that very first year. It was also there that they developed the planar technology, the planar silicon technology, largely due to Jean Arny, the second from the right next to Jay Last in this photograph, which is the basis of integrated circuits today. Well, a number of people stayed on at Shockley Semiconductor Labs, which was reorganized in '58 to be called Shockley Transistor Corporation. Here's some shots of it. You can see the front side. I think that's probably about 1958-59 because Beckerman Instruments is still listed as the parent corporation. And I think the second one on the right, I got that from Hans Queisser, another of our panelists tonight, is about 1960. And they continued on pursuing a what was called the four-layer diode, an avalanche diode that Shockley hoped would become a key device, a key component of the electronic switching systems with the Bell Telephone Labs and the Bell system was trying to bring out at that time. He hired heavily to replace this, turning in many instances to people from Europe. There was Adolf Gutzberger, Hans Queisser from Germany, and others like Jacques Baudouin, who was in the audience, who came in a bit later, I think in 1960. And they really focused on making this four-layer diode in which you had to do your diffusions from both sides of the wafer. It was an incredibly difficult device to make and to make reliably with uniform characteristics, such as, for example, its breakdown voltage. You wanted it to break down at exactly the same voltage from one device to the next. And that proved to be very difficult to do reliably. Well, they had hoped to sell this, like I said, to the Bell Systems, but the company never really realized the profit. It was sold to the Clevite Corporation, which I think is mentioned, is noted here on this slide, in 1960, and then to IT&T, which eventually closed down Shockley Semiconductor Laboratory in 1965. Now, the panelists today have been selected both for their knowledge of the industry and for the breadth of the coverage of Shockley Semiconductor Labs that they represent. The time frame we're really going to be looking at right now is 1955, its origins from 1955 to about 1961, which is really its very creative, productive core. In 1961, Shockley also had a major traffic accident on Highway 1 in Montara. And as far as I can tell, the real creative force behind the company had gone. In 1963, he accepted a professorship at Stanford University, and like I said, the company was closed down in 1965. But the four panelists today range from Jay Last, who joined in 1955, to Hans Queisser in 1959 and stayed until 1963. So let me start by introducing Jay Last. He earned his PhD in physics from MIT in 1956. And immediately after he finished that PhD in April of that year, joined Shockley Semiconductor Laboratories, the fifth employee to do so. He was among those who left in September of 1957 and was thus a co-founder of Fairchild Semiconductor. He headed the Integrated Circuit Development Group that took the ideas of Robert Noyce and turned them into an actual product, which made it into the marketplace in March 1961. By that time, he had left Fairchild Semiconductor and co-founded the Amelco division of Teledyne Incorporated. This is one of the earliest of the Fairchildren. Since then, he has gone on into publishing and is the principal of Hillcrest Press in Beverly Hills, California. And I'll let him tell us his take on Shockley Semiconductor Laboratories. Let's see. There we go.
I met Bill Shockley first in October of 1955. I was just finishing up my thesis for my PhD degree in physics at MIT, I was working then on a problem of infrared transmission of light through crystals to determine the crystal structure. For this, I was using an instrument called a Beckman spectrophotometer, which was sort of beyond Beckman's technical capability to make the instrument. So while I was using this, I got, and there was feedback back and forth with Beckman a lot, and I made some suggestions. So it turned out that by the time I got out of school, or was getting ready to look for finishing my degree, a lot of the Beckman people knew me. And so in September of '55, when Bill Shockley and Beckman signed their agreement, Beckman told Shockley about me. So Shockley flew up to Boston to talk to me about possible employment. I was immediately struck with what a bright mind he had. Some of the ideas that I'd been wrestling with, in 5 minutes he understood what I was saying and made very constructive comments. I talked to him later down in Washington and was very intrigued with the idea of going to work for him. I had been destined to go to Bell Labs. I talked to the Bell Labs people and said I was thinking of working for Shockley. And he said they pointed out to me this was not going to be a bed of roses. So I fed that into the equation. Also, 10 years before that, when I was 16, I lived in Pennsylvania, and I hitchhiked out here to Santa Clara Valley. And I worked for a summer picking apricots and working in a cannery. And I thought this is a marvelous place to live. I also was interested in mountain climbing, so the Northern California appealed to me enormously, as did the thought of working with Shockley. So I accepted employment in December of '55. At that time, Shockley had hired 4 people. These were people that had had some experience with transistors, but none of it at Bell Labs. This was Bill Happ, Smoot Horsley, Leo Valdez, and Vic Jones. By February, when Shockley came, he was still down in Southern California then at the Beckman place, but by February, when he moved to Palo Alto, he had 12 people. He was a very active recruiter at that time. I joined him in April, and there were about 20 people. By June, he had a professional staff of 16 with a support group of 7. The payroll for this group of 23 people was $17,000 a month, which by present-day standards was the bargain of a lifetime. Of these hires, hardly anybody had any experience at all with transistors. And certainly nobody had any experience with using silicon as a fabricating mechanism. So this was all learning on the job. A group of us held study sessions working together to learn about transistor theory. Also, another key thing, Shockley had maintained close relationships with Bell Labs, and we had access to the Bell Labs, a lot of their technical reports, especially things like oxide masking, which were recorded here. So we learned on the job both the theory and how to make devices, a lot of experimenting devices. The theory was so weak then that it was sort of a Thomas Edison approach, just try things and see what worked. The theory caught up with that later on. So it was a great educational experience for a year and a half. As has been discussed, a group of us left in September of '57 after I'd been there a year and a half or so. And I look back, what did we learn at Shockley? Shockley made the two key decisions immediately. One, we were going to use silicon, and two, the devices were going to be made by diffusion, which in hindsight sounds very straightforward. At the time, it was a very revolutionary idea. The other thing we learned was that Shockley was not especially interested in making transistors, but the group of us were. We really thought we could make transistors, and we were determined to do it. And so we left as a group and started a company as a group. But when we started Fairchild, there was a host of tasks that needed to be done. We were essentially research scientists that had to turn it into production engineers. We had to learn to grow crystals without dislocations. We got up to a 3/4 of an inch wafer as a start. We had to turn diffusion from something that would blow up on you if you weren't careful to something that was a reliable production process that could be repeated time and again. We had to develop, we wanted to realize we wanted to make a lot of transistors on a wafer, so we had to develop step and repeat cameras and find a way to keep photoresist from falling off of the wafer. We had the problem of making reliable contact to the devices. You have to make contact to both N and P type silicon with one metal, and that was a major problem. It took a long time. We had to figure out how to put contacts on there, how to package the devices, and to do device testing. And the key thing we realized, we were not going to have a successful company unless we sold a reliable product. And these were all things that took an enormous amount of attention to detail. The first devices we delivered in August of '58, and we announced this device as a product in August of '58. We had been in business by then 45 weeks, and had spent something between $1 million and $1.5 million. Gordon Moore and I have speculated a lot. What would have happened if Shockley hadn't hired us and we started here? It's pretty hard to see how silicon, this area would have turned into a big device-producing area without that initial thing. With Stanford, of course, it would have been a success. But the valley is called Silicon Valley. It's not called Software Valley. No, just one last sentence. But I want to make one last remark. We all owe a great debt of gratitude to Bill Shockley for his pioneering efforts in getting this whole thing started here. Thank you.
The next person I have to introduce is a chemist, and I neglected to mention earlier that this panel reflects this multidisciplinary character of Shockley Semiconductor Laboratories, not just physicists like Jay and myself, but chemists and electrical engineers. Harry Sello got his PhD in chemistry from the University of Missouri in 1948 and was working at the Shell Development Company in Emeryville in early 1957 when he got a phone call from Bill Shockley inviting him to join Shockley Semiconductor Laboratories as a physical chemist, which he did in April of 1957. He was not among those who left in September of that year to form Fairchild, but joined them about 2 years later in April of 1959. He stayed there 2 decades, which is probably, and he deserves an endurance award for that. He is now the principal in Harry Sello and Associates, a consulting firm that has its offices on Sand Hill Road in Menlo Park. Harry?
This is not going to be a talk about how you missed the boat. I want you to focus on a couple of words that were mentioned in the previous speakers, and that's the word chemist. Did you notice that the three top diffusion people at Bell Telephone Laboratories, where Shockley did his best work, were chemists? Talk about interdisciplinary science. I'll never know exactly where Shockley got my name or how he got my name, and I mean that truthfully. I was at the Shell Development Company in Emeryville. I'm a physical chemist by training, not just a chemist, and there's a difference. A regular chemist is a potboiler. Physical chemists boil pots, but they understand them. When Shockley called, I guess I didn't answer the phone immediately, and he said, he asked, Dr. Sello, do you know who I am? And I paused, and it was a painful pause, and I felt I had to say something quickly. He said, yes, I know. You're Dr. William Shockley, the Nobel Prize winner, at about that speed. He said, that's correct. And on the telephone, he said, would you like to come to work for me? Well, here I was at a potboiler organization looking to understand what organic chemists do when I didn't understand. And so I accepted. I had to go through a few little qualifying examinations. First, examination by Dr. Shockley to make sure that he was getting the I think that he was getting the talent he wanted. I've never been quite sure of that. But nevertheless, when I came to work, he introduced me to the other chemist, also a physical chemist, whose name was Gordon Moore. And Gordon welcomed me. He says, my God, I'm glad we've got a chemist here, finally. Because he was a spectroscopist, and I was a physical chemist. But those things were important to Shockley. He said, I want you to take a look at what we do when we etch silicon. I had never even seen silicon. I didn't know what hydrofluoric acid was. And I had never used any of these horrible chemicals that these guys use all day long. I saw Jay Last over in one part of the laboratory, and he was, I guess it turned out he was polishing silicon wafers, little half-inch jobs. And he had one under each finger. And he was polishing them on a lapping plate. And I said, well, that's no deal. He's a physicist. What else? Well, I found Shockley inspirational, brilliant, capable of defining what we in all our sciences call the definitive experiment. If I would lay out a matrix of experiments on how to build a transistor, and I'd make a 10 by 10 matrix and change all the variables in the right way and try to learn the problem, Shockley came up to me one night and he said, what are you doing? He had put me on the assignment late in the evening. And I said, well, I was trying to make that power PNPN that you would like us to make. Now, the PNPN device is not to be understood anyway, as far as production is concerned. You're just almost impossible to make two of them to the exact specifications. You can make them, but for them to fit in electrical circuits, to work as relays, and they should, they have a lot of distance to go, and it just isn't makeable. So I knew that we had to do something special. He said, now in my other hand, I have this black stick, and it looked like a big ebony rod. And what it was a piece of petroleum wax. In the bottom of all the distillation furnaces and whoever distill gasoline and chemicals, left in the bottom as a residue after weeks of distilling is this stuff called petroleum bottoms. Nobody knows what they are. They're dangerous, but a company made a business out of casting black wax rods and selling those to semiconductor manufacturers, because that black wax was totally resistant to HF. And a mixture of HF and nitric acid, which is about as bad as you can get. And so Shockley said, go over to Bob Brown and he'll show you how we work with this stuff. And they take a hot needle and they stick it in the black stick of wax and they make little dots on the wafers that Jay was polishing. And each of those little dots is resistant to HF and nitric acid. And when you etch them, you get round little dots of silicon. He says, now, do you understand what that material is? God, I came from Shell Chemical. And we were blowing up stills by distilling that kind of stuff. And I said, well, yeah, we work with that up at Emeryville. He said, we need a substitute for that. He says, this kind of crud just can't last in semiconductor work. I'll let you know that Fairchild later, in its great successes, made its first integrated circuits using little black dots of wax, for which they sold their flip-flops for an untold amount of money. And it works, and it worked then, and it works today if you want to do it that way. I was given the job of finding a substitute. That was my first job at Shockley. Find a substitute for this black wax. And I must have tried about 50 to 60 different varieties of things we call carnauba wax. And you know what carnauba wax is. It's an impossible material. You heat it up in a crucible and you pump on it in a vacuum system and you let it evaporate. And hopefully it'll evaporate through a screen in little round dots. Well, we worked on that. That was my first job at Shockley. Total failure. Total failure. The evaporated wax didn't resist HF and nitric acid worth a damn. But it sure resisted black wax. And that was my first job. And it was a failure. After that, I saw Bob Noyce getting very tired of working with Kodak photoresist because it wouldn't stick on the silicon, and he chased me into the laboratory as his assistant and said, go make it work. I can't. I didn't either, because Kodak photoresist is not built to etch silicon. Other resists have been invented since then that are much better. But I wanted to illustrate Shockley's mind in a different way as a last anecdote. Thank you, Michael, for reminding me. He called me into his office a number of times to try to explain things, and he was brilliant at explaining things. And one time he called me in and he said, by the way, you published a paper on the detonation limits of petroleum products while you were at Shell. I'd forgotten about it. It was one of my first papers there. And he said, what was that all about? Explain it to me. And I explained. I won't go through all the details. But one of the things that you do in laying out the data is you lay a triangular plot, an equilateral triangle. And all the sides, when you plot things on that triangle, have the property that they all add up to 100%. So you can add all the little combinations of things on that triangle up to 100%. And that was the basis of my paper. And I started to explain to him what detonation meant and all. He said, look, don't bother me with that. I know what detonation means. He said, what I want you to do is mathematically derive for me why that triangle sides all add up to 100%. Wow. Out of left field. I mean, that's a piece of graph paper. And we use it all the time. Most people use rectangular graph paper. We happen to use triangular graph paper because all the sides of a triangle, when proportionate, will divide up and add up to 100%. And he said, I want you to derive for me that works, because if that doesn't work, you can't prove it, then you didn't do any research. Well, I struggled for about a half an hour. I worked my way through it. And he said, well, I won't argue with you, but you missed a few points. But good enough. That will work. But that was Shockley. And one last question I'd like to point out about his mind. He said, you also have a couple of patents. Yes, I do. And on one of your patents, there are 3 people listed. And tell you the truth, I don't even remember their names. I know I was alphabetically the last one on the list, Sello. And he said, why do you have 3 names on that patent? I said, well, because we all participated in the invention. It was the way we learned how to stop detonations. And I looked at him, and I saw that wasn't the right answer. He didn't like it. He said, well, which one of you did the invention? I said, well, no, we all participated. I did a part, they did, my partners did a part, and we all applied for the patent, we all 3 got it. He said, but yes. He said, on a patent, there is one mind in which the bulb lights up. And when the bulb lights up, that's the guy who wrote the patent. What you ought to do is go back and decide which one of you deserves the patent.
We're getting on in time. We had intended only to take 5 minutes per panelist here. We're going way over that. I hope the audience will bear with us. Our next speaker, next panelist, you like this? Okay. Well, I'll be here a little bit longer. Our next panelist, Jim Gibbons, received his PhD in electrical engineering from Stanford in 1956. I think he was the first graduate of a program to build transistor circuits in the laboratory at Stanford. He held joint positions at Shockley Semiconductor Laboratory and Stanford as an assistant professor of electrical engineering beginning in August of 1957. He came there just as the 8 were exiting the next month. Since then, he has served as Dean of Engineering at Stanford and is now Dean Emeritus.
Thank you, Michael. I'll try to do 5 minutes. I want to focus my remarks on the contribution Bill Shockley made to the creation of the solid-state device laboratory at Stanford. Stanford's program began when Fred Terman hired John Linville from Bell Laboratories to come to Stanford and, as he said, transistorize the curriculum. That was in 1954, March 1954. John quickly recruited several graduate students, and we set to work on various circuit design problems. I was John's first PhD student, as Michael said, finishing in 1956, just a few months after Shockley had established his company in what the mayor of Mountain View calls the city of Mountain View. Not Palo Alto, that's all. Several months later, toward the end of 1956, John arranged a meeting with Shockley to discuss how Stanford graduate students in electrical engineering should be educated for productive careers in what was clearly going to be the world of semiconductor devices. Shockley's recollection was that during that meeting, he suggested that Stanford should build a laboratory where graduate students could do experimental device research, not just circuit design. He also said that if Stanford were willing to do that, he could teach a faculty member what he needed to know to build such a laboratory. It's also clear that John Linville himself had that possibility in mind when he set up the meeting. In any event, sometime in the early spring of 1957, I received a letter from John proposing that I come back to Stanford to start this new lab. He indicated that Stanford would allow me to work with Shockley for half-time for 2 years to learn what I needed to know. I was in Europe at the time on a year's study at Cambridge University and was expecting to return to Bell Laboratories where I had an appointment. But I decided to come to Stanford instead to see if we could build a successful device research lab. My wife and I thought it was worth a try. That was 49 years ago. I started work at Shockley on August 1st, 1957, as Michael said. On my first day there, after some rather unusual preliminaries that included Shockley's idea of an IQ test, he introduced me to his excellent team of employees and told me how he liked for people to work. To carry my weight in the lab, I was supposed to spend some of my time designing circuits for PNP and diodes, while I also learned what I needed to know to establish the lab at Stanford. My coaches were an outstanding group of people. Bob Noyce got me started in device design. Gordon Moore was my coach in diffusion. And several technicians, some of whom are here this evening, helped me understand how to build and set up the equipment I would need to set up the lab at Stanford. 6 months later, the Stanford lab was up and running. We had made our first low-loss p-n junction diodes for use in parametric amplifiers. We were a year and a half ahead of the schedule that had been set out for us. As it turned out, a significant part of my laboratory education program was overseen by Bill Shockley himself, for reasons that could not have been anticipated when I joined. What happened, of course, is that about 2 months after I arrived, the 8 senior scientists at Shockley's who formed Fairchild left for that purpose, and I was then left without coaches. So at my weekly meetings with Shockley, we first discussed my progress on circuit design for PNP and devices, and then we turned to the problems I was having building the lab at Stanford. He was full of suggestions, ideas about things to try, things I should read, people I should talk to, and constantly encouraging. And through it all, including the upset that he had with the Fairchild folks leaving, he continued to write scientific papers, on some of which he asked me to be a co-author. It was positively exhilarating time for me. I continued to work with Bill for 4 years after my device apprenticeship. I learned an enormous amount from him during this entire time, often over hamburgers at Kirk's, where he wrote on napkins, with equations that often circled hamburger drippings. I was constantly impressed with his truly extraordinary gift for creating quantitative models that could capture the essence of really difficult device physics problems. He was really brilliant at that, uniquely so in my experience. I wish I'd saved those napkins. So here we are, 50 years later, gathered in part to honor Shockley's legacy. Where Stanford is concerned, what Bill did was succeed in helping us implement what I will say is the Linville-Shockley vision for a futuristic electrical engineering department, in which graduate students were educated to use state-of-the-art silicon fabrication technology in their research. Bill knew what had to be done, and he knew how to do it. All Stanford had to do was apprentice someone to him to learn the technology and transfer it back to the university. Thank you.
And finally, we have Hans Queisser, who joined Shockley Semiconductor Laboratories in October of 1959 and stayed through 1963. He received his doctorate in physics from Göttingen, and particularly in solid-state physics, and joined Shockley to work on the physics of silicon. After his tenure at Shockley Semiconductor Laboratories, he joined Bell Labs in 1964 to 65, working on what we now call light-emitting diodes. He was the founding director of the Max Planck Institute of Stuttgart and is now director emeritus. Hans?
I was born in Berlin in 1931, survived the various air raids of the Second World War, and wanted to study physics because I felt if you have something that is of interest to others, for example, the Russian or the American occupants, that can save your life. But also, since my father was an engineer at Siemens, the natural sciences came naturally for me. So I did my work first at the university in Berlin. Then I was extremely fortunate to get a scholarship as an exchange student at the University of Kansas in Lawrence, Kansas, at the time when they became basketball champions and went to Helsinki. Wonderful, nothing against the people in the Midwest, friendly and nice. But of course, it got me acquainted with the American way, with the English language, American English. And after I got my PhD in looking at defects in metallic and other systems, I wanted to come back to the United States. So I applied, but most people answered, no, you have to be a U.S. citizen in order to be with our company. But one day, one of my professors came and said, I've met Shockley at a conference in England, and he said, don't you know anybody who might work on defects in silicon? And this Professor Leibfried said, yeah, I think I have a guy there at Göttingen, and said, why won't you try to join Shockley and work on defects? You see, defects were very important for understanding what was going on in the Shockley 4-layer diode, because only in silicon it will work. The silicon p-n junctions with defects are non-ideal rectifier equations relating current and voltage, and that was the principle of the bistable switch. So we had to understand defects and their charge state and recombination properties. So, okay, I said yes, I come. Shockley wanted me very quickly for 2 projects. Was a little bit difficult for me to get the visa and the green card, so he wrote a letter to the Secretary of the Air Force. He then wrote a letter to the consul in Hamburg. So I went there, got my green card, and off I went, and arrived here. Kurt Hubner, from whom I extend greetings, Swiss guy, a constructive pessimist, picked me up at the airport, which was much smaller, of course, at that time, and said, well, we don't know, we might go bankrupt next week or the week after, but we can go over to the Fairchild people, they'll take us. I thought, not me, because I hadn't heard about semiconductors in Göttingen. So I had purchased Shockley's book, Electrons and Holes in Semiconductors, and struggled through it. But all right. So then I went and we arrived at 391 South San Antonio Road. And I said, this is it. This is the laboratory of a Nobel Prize winner. But all right, I said, okay, here I am now. And I started. So Shockley said, you're responsible for 2 projects. One was making a multi-cell solar battery. 70% of the money was spent, but maybe something like 15 to 17% of the results were out. So I worked very hard, and I made something, diffusion from both sides, which was really a first integrated circuit, but with a lousy and non-usable technology. But at least I got 10 volts out of the solar battery. Had to come into the labs at night and so on. The other one was a more theoretical thing that Shockley said, let's work on it. The United States Air Force, this was, of course, the time after the Sputnik shock. Very, very tight race there. And the Air Force people wanted to know, what is the best material for a solar cell? And what's the maximum efficiency you can get out? Before that, people just said, well, so much sunlight coming in and so many losses and all that. Terrible. Not a scientific attitude. Shockley didn't like that, and so we worked on it. I didn't have a computer, but I had a nice slide rule. So I did lots and lots of calculations. We wrote a little paper, submitted it, and it came back, and boy, did I ever see Shockley mad. He came in steaming mad and said, look, Hans, look at this letter. They rejected our paper. Huh? But we sat down, did a little bit more work, explained things a little bit nicer, submitted again, and, well, they accepted the paper. Nobody really quoted it, but nowadays, with the new programs on solar cell, the paper is being quoted all the time. It's a 61 paper. So it's really something. Makes me very happy. So, and Shockley, when I last spoke to him in the men's room, but it's true, of the Stanford Faculty Club, he said, you know, Hans, I think we did something really useful. This theory on the solar cells, now people begin to believe it. So I worked on many things like dislocations, diffusion, down grain boundaries, want to make a very narrow, rapid transistor. Things had changed. Shockley now needed money from government contracts to do research. He didn't want to make any transistors, nor did he want to make any solar cells. But silicon was the choice material for solar cells, and we could learn about silicon, about the forward characteristics, the IV characteristics. So I worked on that, and we had great fun. And later on, when I went to Bell Labs, he became an executive consultant. So I had another 2 years. So all in all, I had about 6 years of very close collaboration encounters with Shockley. He was indeed a genius. Very quick, immediately recognizing the things, but also very impatient. He would call me in the afternoon from home and said, Hans, we'll make this such and such an experiment. And next morning at 9:30, he came in and said, have you done this experiment? So he was a theoretician and didn't quite appreciate the difficulties. We really had difficulties in those early years. Making a hard p-n junction in silicon, you wouldn't believe it. And the black wax, of course, I used too. And the Kodak photoresist I used too. So I owe him a great deal. And people now say, Shockley is the Moses of Silicon Valley. He showed the way to the promised land of a new technology, but he didn't reach it himself. So I'm very grateful, like most of us who work with him. Thank you.
Well, given the fact, is my mic on? Given the fact that we've all exceeded our time limits on this, I think we're going to have to foreshorten the panel discussion portion of this so that the audience will get a chance to ask some questions on their own. So I'd like to just begin this by noting that there have been several observations about the unique Shockley personality. And I'd like to throw out a question. How do you think that personality influenced the course of events at Shockley Semiconductor Laboratory? Harry, would you care to field that one?
Which laboratory? I'm sorry.
At Shockley Semiconductor Laboratory. The course of events.
In my experience, what Shockley did for me was to force me to think analytically. I thought I was thinking analytically originally. After all, physical chemists do that. But when Shockley examined a set of experiments that I was trying to do to make a device which was analogous to his PNPN switch, but one that now would carry power, meaning larger silicon pieces would be involved at least. And I set out a series of experiments, 10 by 10 matrix, I mentioned this in passing. He came by, and it was about 11 o'clock at night. He came by, and how you doing? I said, well, here's the apparatus, and here's the heat dissipation sink, and here's all the stuff I'm going to be using. And then he said, what's that chart you have? And I had this, one of these charts laid out, we all know them now, of a series of experiments. If these two worked, you tried the third. If they didn't work, you went to a fourth, and then came back to the first two, this sort of thing. He said, no, you're wasting your time. What you do is choose the experiment in the upper left-hand corner, the second one in the upper right-hand corner. If those two don't work, choose the third. If that doesn't work, forget the project. Whoops. Forget the project. I really worked like a slave figuring out the factorial analyses of these experiments and how each one would work or not work in the face of its neighbor. No? And I did that. And sure enough, the third experiment didn't work. Forget the project. Work on something else. And he left. Unfortunately, that period in Shockley's era was just shortly after my new colleagues had just left to form Fairchild. And he disappeared. He was so concerned with making PNPN diodes, the device that he wanted to revolutionize the electromechanical switching of telephones, with which he wanted to do that. He was so focused on that he disappeared from view, from me, from Dr. C.T. Sa, who was one of the most brilliant MOS transistor device manufacturers I ever met, and designers. And he disappeared, carrying on the work with the PNPN diodes. The attention span wasn't good. And being a novice,
we had to find our own experiments to perform without the full realization of would Shockley bless these or would he not bless these? And that was very important to us. Didn't happen.
But what was it that led the 8 to decide that they had to go off and form their own company? I guess Jay Last is in the best position to answer that question.
I think Jay is much better in position to do that than I am.
We had a difference of opinion with Shockley. Shockley wanted to focus on the four-layer diode. We wanted to make transistors, and we could see that we were at an impasse there. We were finding it more and more difficult to work with him on this level, and so to focus ourselves and to do what we really wanted to do, we were going to leave individually, for each of us for our own reasons, and we decided to make an effort to work to find somebody who would hire us some company would hire us as a group. We approached some Wall Street people who said the way you do this is start your own company, which was a novel idea at the time. It was really the start of venture capital. But it was really our difference, the way we wanted to work, rather than all reporting to Shockley and Shockley being the symphony conductor. We wanted to work together as a group, so we changed our way of working completely from one-to-one thing where we were technically sort of isolated from each other, where we worked on a minute-by-minute basis together in a cooperative way.
Wasn't it also the fact that Shockley was very much focused on research as opposed to development, that getting a product out the door was not a top priority for him?
No, it was a top priority. It was a top priority for him, but he was so caught up in research understanding that it didn't always come to pass that way.
Michael, I'd like to add a view of this. Bill had two things he was trying to do. One of them was run a successful company. The other one was maintain his first-class scientific reputation intact. And the way that worked out was, we would prepare ourselves to go to the National Electronics Conference, let's say, in Chicago. Lots of P&P and device applications. We had a nice booth. We set up, and we, as is usual, welcomed people into the booth and talked about all the wonderful things we could do with P&P and diodes. And somebody would show up at the conference, one of Bill's physics buddies, and say, gee, Bill, I see your company's going pretty well, but I haven't seen anything published in the physics literature recently. A couple days after you get home, now you're working on phonon drag. And now, well, we're going to write a paper on phonon drag, or we're going to do some real fundamental work on solar cells, or whatever it is. You're not working on P&P and devices and circuits and so on. We kept being jerked back and forth about every 6 months, depending on, and then you go to a physics conference and, hey, you're writing great papers, but I see your business isn't doing too well. Okay. It was tough. If there's any lesson that all of you who've run successful businesses know, it's focus, 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 right? This was not Shockley.
Yeah, I mean,
We really believe that the science was the major thing. And he once told me, Hans, you go out to the production engineers and lecture to them what a p-n junction is so that they understand that, because if everybody understands the basic physics, we just have to make a profit. Of course, that wasn't true. And it was tragically untrue. But he always said there is the importance of the respect for the scientific nature of practical problems. He preached that all the time. If you have a practical problem, take a scientific attitude and solve that problem, which in the production environment is not by necessity true. And there's a certain tragedy in that, in the personality of Bill Shockley, that he thought that by just doing good science, you are bound to have a profitable company. Not true.
I mean, it really strikes me as a historian of technology that it was very clearly stated in the original contract between Beckman and Shockley that the purpose of this company is to make diffused-based transistors. But by 1957, that was not a challenging enough project. And that is essentially what Fairchild Semiconductor went out and did, the original goal of Shockley Semiconductor Laboratories. Shockley had moved on to a more difficult and challenging project, the PNPN transistor, which never, PNPN diode, which never really made it as a successful commercial product.
But of course, it was the same project that he started out at Bell Labs right after the war. And the Bell Labs boss at that time said, Shockley, you create a group and you find a better switch. And it looked to him that the bistable diode, just two contacts, was the thing. Bistable and a two-terminal device. Difficult to make and even more difficult to make sensible circuits out of it, right?
Well, I think given the lateness of the hour, it's about time to open it up to general discussions. And if anybody has a question, please come to one of the mics that are located here. If you have a question for Jim Gibbons, who has to leave due to for personal questions, could that person ask a question of him first?
What was the work ethic like there at Shockley? You mentioned working at 11:30 at night. How many hours were you expected to be working during the week?
Well, since I brought that subject up, I ought to answer that. Shockley had no hours. Just had no hours. I got called at about 9 o'clock at night, and I was in the laboratory on that particular project by 11, starting to build that PNPN power device. My time was and I didn't really mind it. My time was at the disposal of the Nobel Prize winner. If he thought, that's the way I felt personally, if he thought that I could do something that would be useful with my little brain and my chemist's thinking, if you will, then I thought that I should give it a try. Little did I know that it was not makeable. I didn't know that as far as the knowledge of silicon junctions were concerned. I learned that in many other hard ways later, at Fairchild and other places. But I didn't know that then. If Shockley thought that that diode could be made with two parallel junctions from two completely parallel flat sides of silicon at the same time, that wasn't my problem. If he thought so, it was worth doing. He had such a keen analytical mind for it that it would go a long ways before I would challenge it.
Yeah, I'm curious, probably for Jim, that, from a circuit standpoint, you really want a three-terminal device with input-output isolation and a control. And knowing Bill, and his tremendous intellect, I was always curious why he had just this incredible brain lock almost on the four-level diode as opposed to a transistor and developing that.
I think, Jim, it had significantly to do with the principal application that he hoped to sell it into, which was a cross-point switch in the telephone system, where two wires came together and you wanted to make a connection between this telephone line and this one. You needed to create a short circuit at that point, and two diodes, a two-terminal device that you could pulse would turn on and then pass enough current through it to keep it on, was the simplest possible solution if you could make the device and give it exactly the right properties, consistent properties device to device. So the complications involved in doing it were things that one could surely solve. It was in some way the beauty of the answer that he thought was the reason that this would win in the end. The fact that you couldn't make it was another issue, so you ended up trying to do all kinds of circuit tricks to avoid the fact that they all didn't have the same switching voltage and the same holding current, and just on and on and on and on. But there was something that Bill had a sense of what was beautiful. And that's what he wanted you to work on, was what was beautiful. He had a sense of this system and how beautiful it would be if you could make these diodes. And
beautiful and simple.
Yeah.
He wanted something
conceptually
new.
simple.
Conceptually simple. He wanted something new.
Yeah.
The transistor was...
And that only he could make.
And that carried his name, the Shockley 4-layer diode.
Yeah.
We're talking around a point here. Jim mentioned it, and I'd like to cap the talk with something else about Shockley that I learned. If someone else succeeded in making that 4-layer diode, before he did, he would have dropped it like a hot potato. He did not believe in working on devices which somebody else had made because he wasn't the first. And that came through to me, my colleagues may or may not agree, on the 4-layer diode. If he could make that and really make it in high yield, low cost, so that Bell would beg for the device to replace their electromechanical relays, and he'd be the only one in the world that was making that device. And that was his driving force, one of his big driving forces.
I agree completely. Yes, sir.
Well, maybe that was the problem with the diffuse-based transistor, because wasn't Texas Instruments beginning by 1957 to have diffuse-based transistors in production? Jay, do you remember that?
It was never a major factor, I don't think, in his thinking. TI's efforts were not.
Sorry, Jay. I had a question about the departure of the 8, because it seems to me that you all bring different perspectives here. I'd be interested, Jay, to know what sort of relationship you Fairchild founders had after the break. And Harry and Jim, I think it'd be interesting to hear whether you saw any changes in Shockley and how he reacted, and whether you saw any changes in how he ran the company. And then Dr. Queisser, what you saw, whether this sort of shadow of his lead scientist having left in any way, left a legacy that you felt influencing the environment when you came.
Shockley never spoke to me after I announced I was leaving.
I had another reaction as well. He spoke to me because I stayed there. And I felt appreciated because I had been hired for certain skills that I thought I had. I learned a whole batch of new ones. But Shockley's attitude changed markedly. There was no question that a bunch of good scientists leaving as a group really impacted him. It impacted me. It impacted others. So that he felt that I think it was a sense of desertion, that really he maybe wasn't understood. And it showed. And it showed in the way in which he worked in the laboratory. We had 2 locations. One was at the Beckman building, Beckman Spinco division, where the production was for the 4-layer diodes. There was no production for 4-layer diodes at the Mountain View location. There was none there. It was all transferred over to the Spinco division. And the rest of us, Dr. C.T. Saw, Dr. Sam Folk, who is sitting here tonight, I think he would bear me out, we sort of felt left out of things. there was certainly, we felt there was something we could do, even to help PNPN diodes, though I, for one, was convinced that we just weren't going to get there. There were enough people working on that. Shockley did not pay much attention to the people, the technical guys left working at the semiconductor laboratory in Mountain View. He was busy doing other things. I'll give you one example. C.T. Saw and I organized a series of teaching lectures for new technicians and new engineers to bring them up to speed on PN junctions and their leakage and their defects. Now, C.T. Saw was brilliant at this, far more brilliant than I am. He was good, and he was a good lecturer, and we organized this class. The class met 8 o'clock every day, and it met for a period of about 3 weeks, and I thought, each one of us had a part. Saw had his part of design. I talked about processing. We were going to go on to things. Shockley came in one day, and he said, what are you guys doing? I can't find anybody in the laboratory. This was 8 o'clock in the laboratory. I can't find anybody. And he was serious. I said, well, I spoke up. Saw is a very, very quiet, diffident guy. Nothing about Saw except brilliance. And I said, well, we've got this class going. He said, well, dismiss it. And I said, okay, I've got some things I want to talk about, and I'll be back in here later. I want to tell you about some other problems we have. He never came back. I know, now this is my personal feeling, and I don't want it to reflect on Jay Last or any of the guys here on the podium. My personal feeling was that this was his field, to explain PN junctions in any format to anybody who wanted to know. This was not the purview of Dr. Harry Sello, nor the purview of Dr. C.T. Saw, nor even later when he invited the manager of the Spinko work to come over and talk, and that didn't work either. There's an ego here. There's nothing wrong with it. It's just a personality.
I think Shockley was devastated, Leslie, when the Fairchild 8 left. I was on both sides of that transition, not much on the first one, but quite a lot on the second one. And my interactions with him were intense. He was very anxious to prove that he could reestablish a team that was just as good, person for person, as the Fairchild guys. And he did, from my point of view. One of them's on my right. The people that came in after the Fairchild guys were equally brilliant. They did work on the things that Shockley wanted them to, and the Fairchild guys decided we're never going to get anywhere that way, so they went on their way. So there was a difference. Shockley knew what he was looking for the second time, people that would do what it was he wanted them to do precisely. Now, that's not a rub one way or other. It's just Shockley understanding about himself something that perhaps he didn't understand as well as he should have when he hired the original team. But I can remember, I won't quote these memories because I don't think it's appropriate to do it, but there were lots of times when Bill would talk about, we're going to beat those guys. We're really going to beat those guys. And here's the way we're going to do it. And he did end up, by the way, eventually. Bob Scarlett, in fact, came and worked for him full-time for a while, building very high-power silicon transistors. He did build transistors. But it was
Cleveite wanted it.
Cleveite wanted it, and finally he did this. But intensely competitive, and when the group left, his first job was to go find 8 others and say, okay, now we're going to beat you. That's Bill.
You've been patient. Why don't we take a question from this side of the room?
There was a term that was probably coined by someone, and I have no clue, that the 8 who left were known as the traitorous 8. What were your feelings when you heard about that term? And I have no clue as to who coined that. Might have been someone outside. How did that strike you?
Oh, it was a term that I didn't hear for many years after that. It was coined, I think, by somebody in the press years later, and it was a term that caught on rapidly.
Well,
it was a term I wasn't especially fond of.
I don't think so. My recollection's quite different. I remember Shockley calling them the traitors, if not the next day, pretty soon after. He was not happy with these guys.
And his wife wasn't either.
And his wife wasn't either happy. They did very well on those IQ tests, however.
I felt that we could make transistors, two-layer devices, rather. We could make transistors with ease, with our left hands, from the technology, if nothing else, that was available from Bell Telephone Laboratories. From the work of Fröschenderich, of Leigenza, of Maury Tannenbaum, and all of those, who, by the way, at Bell Labs, mighty Bell, have never succeeded in making a silicon integrated circuit. Never.
Well, not quite. But
In those years.
in those years, yes.
In those years. They came up on it later.
That's quite right.
But they did not make it when they had the original technology in their hands.
Yeah.
They weren't interested, or whatever the reason was. But I was impressed with the fact of the teamwork, and I thought energized by Shockley because he was the team leader. The teamwork that guys like Jay Last and Sheldon Roberts and Noyce and Moore had among themselves to understand the problems and divide them up the way they had to be divided up as a leader should do to solve the problems of transistors. They had it down pat.
And at Bell Labs, there was a difference between Murray Hill and Allentown.
Well, that's another Bell Labs. But you asked the question about what was our impression of the work of these guys. They knew where the problems were. They went after them. And they tried to convince Shockley in the short time that I overlapped with them that they knew how to do this and it could be done very easily and cheaply and make a lot of money. And they were right.
Which we proved.
Which they proved.
Let me take a question over here.
Last
Question,
question.
but an anecdote. I've never met Dr. Shockley, but I followed in his footsteps literally once. In the upstate New York, there's a rock climbing practice area called the Shwangunk Mountains, where climbers from all over New England go to learn to climb, to practice. And in 1960, I went up a climb once that was well known among the climbers in the community, where you go up a vertical crack, and if you put your feet in just the right place and squeeze up under a horizontal ledge and reach out 2 feet and up, you can find a handhold to enable you to go up over it. And I always wondered about the nerve and audacity and skill of the first climber to pick a route directly up over the biggest obstacle on the mountain rather than around it. And that route is named Shockley Ceiling after the first climber.
Thank you.
I have a question for the panel. I graduated from University of British Columbia in 1959. I worked for Beckman Instruments in Fullerton, and I joined Fairchild in April 1963, and Dr. Sello remembers me. And I struggled with electron and hole semiconductors. My question for the panel is, why didn't Shockley get Nobel Prize for the theory of p-n junction?
Well, he did.
He did. He did. He did get the Nobel.
No, nobody got Nobel Prize for the invention of for the theory of p-n diode. I read your book, Crystal Fire. You even signed it for me at one time. Okay. And there has not been given Nobel Prize for for the discovery of, for the invention of p-n diode.
A lot of things.
For the transistor.
The prize was given for the junction transistor.
For the transistor, yeah.
I think Shockley's invention of the junction transistor was
Yes.
included under the rationale,
Yes.
as part of the rationale for his sharing in the prize.
Yes.
We don't really know the answer on that because the archives of the Nobel Institute are just now becoming open. They're closed for 50 years after the awarding of the prize. But that'd be an interesting question to go into. I mean, he was also the leader of the group, and the management of effective scientific institutions, I believe, is worthy of the same awards as the actual people who do the work. All right. Let me close by noting what Harry was just getting into, that I think Shockley Semiconductor also had a cultural impact on the Valley. He said, talk about these, his colleagues developing new ways to work among themselves to work out the problems, and then they eventually went off and set up Fairchild Semiconductor. I think this really was a new phenomenon in the mid-1950s in the American industrial scene. And most of this egalitarian approach to doing technological work was probably done at Fairchild Semiconductor, but I think it actually began at Fairchild, at Shockley Semiconductor, and then transmitted to Fairchild later on.
Michael, Jay, Harry, and Hans, thank you very much for a wonderful evening, and we really want to thank you for the terrific time. And I'd like to also especially thank all the employees for making this 50th anniversary very, very historic and very, very special. And keep in mind, in 2007, we plan on hosting a Fairchild reunion here at the Computer History Museum. So come back for more, enjoy yourselves, and thank you so much for a wonderful job.